And in the second stage, we use the addition of pure elements and H2 precursor powders and flat rolling induced CX texture. The Jc is quickly increased to 10,000 ampere per centimeter square at 10 Tesla. And we use hot pressing method to synergistically increase cool density and texture. So the Jc is increased above the level for practical applications. And now the study of iron-based conductors have entered to the practical research. The multifilamentary wire tapes have been fabricated, and we use low-cost sheath materials, and we study the strain, stress properties, and ACLs, as well as the pinch behavior. And we fabricate a 100 meter long wire, and based on the wire, we study the mounting joints and the iron-based mounting coils. Okay, there are two key problems for the PIT wire. The first is low density, and you can see here the cracks and the pores, which they largely diminish the actual cross-section area of the Jc. The second problem is the weakening behavior, and as you can see here, the Jc quickly decreases with a very small field. And there is hysteresis of the GCB curves. So to address the fourth problem, the low density, there are several different ways to increase coil density. For example, the high pressure sintering, including the hot pressing, the hot isostatic pressing, and stark plasma sintering. And take the FPS, for example, they can achieve a very high density, larger than 95%. And on the other hand, deformation aided classification of the high strains outsheets can be used. And high pressure is not required, and this tape is centered at ambient pressure. And the vehicle hardness is comparable to the wires fabricated by the heat process. And in 2018, we succeeded in fabricating high Jc mounting tapes at 4.2 Kelvin. IC is 437 ampere with a very small anisotropy parameter. And the corresponding Jc is 0.15 milliampere per centimeter square. And even at 18 Tesla, the Jc is as large as 0.1 milliampere per centimeter square. And for the EBSD measurements, we found C-axis texture, but there is no apparent in-plane texture was found in the filaments. And we continue to study the GCB curves at different temperatures, and we found that the Jc is 54,000 ampere per centimeter square at 20 Kelvin and 5 Tesla. It suggests that the iron-based mounting tapes can be used at a medium temperature region by cryogenic cooling system. So for the hot pressing method, not only the coil density is enhanced to guarantee a good conductivity, but also the texture is also improved. So the statistic increase of these both parameters induced high Jc. But hot pressing also cannot use in the long wire fabrications. So we use groove rolling plus hot isostatic pressing to fabricate the long round wire. The heat process was conducted at 700 degrees, 150 megapascal for 4 hours. And the Jc is as large as 47,000 ampere per centimeter square. And because of groove rolling induced texture, this Jc is increased by 5 times. And the 7 filament wire and 9 filament wire are fabricated And the Jc is 33,000 ampere per cent square. And also the taping tube method, the Jc is in a similar level. We also fabricated the copper silver sheath bearing 1-2 tapes. And the flat rolling induced well-textured grains, and the heat process guarantee a high core density. And but the sintering temperature is limited by the melting temperature of copper silver alloys. Anyway, the Jc is enhanced to 110,000 ampere per cent square. So this process can be cost-effective and scalable to long-wire productions. And here I compare the hysteresis of GCD curves for the hot pressing and hot isostatic pressing tapes. As you can see here, for the hot pressing tape, they have a good CSE texture. So the deviation point of the increasing and decreasing field start at 6 Tesla. But for the hip tape, they have a worse CS texture. So the deviation starts at below 16 Tesla. So the texture is very important for the Jc enhancement, and there is still much room for the Jc improvement. Instead of the hot pressing, we also fabricated the 1-2 tapes using the high strength outer sheath. The stainless steel silver composite tape achieved the high Jc, about 80,000 ampere per cent square, and 4.2 Kelvin 10 Tesla. And we have fabricated a 1 meter long tape, which has a very good homogeneity and high N value. However, through the scanning transmission electron microscope, we found that many grid boundaries are contaminated by the barium oxide impurities of the iron arsenide wetting phase. So the supercurrent may bypass the bad grid boundaries. To study the grid boundary properties, we fabricated the tapes with different potassium doping content, and we found that there is a high Jc above the level of practical applications at the slightly overdoped tapes, and we found a continuous increase of the grid boundary transparency parameters with doping. And based on the proximity effect induced as soon as Josephson junction, we suggest that potassium doping will enhance the proximity effect and consequently the integrate Jc. So here is a simulation for the iron-based melting tapes. For now, the grid boundaries are actually contaminated by iron arsenide wetting phase, which not limiting the intergrain current transport. But we use a slightly overdoping method, found a very good way to enhance the Jc transport. But clean grid boundaries without any impurities is always the best choice. And we hope nearly 100% grid boundary transparency parameter may be achieved in the grid boundaries without iron arsenide and with small instrumentation angle. But how to remove the iron arsenide wetting phase is still a question. But recently, we have used a special technique to remove the iron arsenide wetting phase, and we get a new record high Jc in the stainless steel composite tapes. At 4.2 Kelvin and 10 Tesla, the Jc is enhanced to 0.22 milliampere per cent square at 10 Tesla. And even at 27 Tesla, the Jc is larger than 0.1 milliampere per cent square. And what is more important is that this Jc is larger than the weak field direction of bismuth 223. And moreover, because we use this composite structure, they have high mechanical strength and low material cost, and this fabrication process can be scalable to long-length tapes and very promising to be used in high-field magnets. And here I present the development of transport critical current density. And from 2012, the Jc is only 1000, and after years of development, the Jc of the tape form decreased to 0.22 mean ampere per cent squared. And also for the round wire, it increased to nearly 70,000 ampere per cent squared. Also, it is close to the tape form, and even at a very high field, 27 Tesla, the Jc is above the level for practical application. So our next target is to increase Jc above 0.1 megampere per cent squared at 30 Tesla. But to do this, several problems must be solved. First is how to make clean gray boundaries and how to improve the gray texture. And after these two problems are solved, we can continue to increase the flux pinning force. For example, to decrease the grain size to enhance gray boundary pinning, or by increase the pinning size. For example, by the neutron irradiation, the Jc of the single crystal can be enhanced by several times. So this is a very good way to enhance the critical current density. In my second part of this section, I will talk about the important properties related to the practical applications. And firstly, we cooperate with the Institute of Plasma Physics in China and study the strain stress properties. We found the same reversible compressive strain limit for the single core tapes as well as multifilament tapes, about 0.6%, but the tensor strain limit is relatively low. For the 7 cores tapes, the tensor strain is 0.4%. But this value is close to the bismuth iron-based mounting wire tapes as well as MGD2. And we changed the outsheath from silver to monaire alloys, and we studied the compressive stress, and we found almost no Jc degradation up to a compressive strain of 0.6%. So the IC of the wonderful tapes exhibits less strain sensitivity than the niobium 13, which is very important for the ether application. The binding tests have been conducted by several groups. For example, Professor Hua Liu in the Institute of Plasma Physics, they found the iron-based mount tapes have a binding diameter about 44 centimeters. And Professor Makula's group, they study the binding diameter of the stainless steel silver tin composite tapes. They found even smaller binding diameters, about 2 to 3 centimeters. And Professor Tamakai's group, they study the binding strain of the copper silver round wire, and they found below 0.2% of strain. The IC remains 100%. And also the Institute of High Energy Physics in China, they studied the binding test on the 100 meter long 7-core tapes. In this special device with different binding diameters between 10 to 30 millimeters. And this device was centered at 880 degrees for 1 hour and they are mounted on the precoilers to measure the Jc at 4.2 Kelvin and 10 Tesla. So they found that there is a very slow decrease of the IC retention, and the ratio remains above 80% when the binding diameter is larger than 15 millimeters. But below this level, there is a sharp drop of the critical current. And the AC loads is also very important for applications. And Professor Kovac, they study the AC loads of the single core tapes and the 7 core tapes. And they found that there is a large eddy current in the single core tape because of the highly conductive silver sheath. But after they substitute the silver with the silver tin out sheath, the AC loads is reduced by 15% at 20 Kelvin because silver tin alloy they have negligible eddy current caused by more resistivity. Okay, the thermal conductivity of the experimental tapes are also very important, and we found that the thermal conductivity are dominated by the sheath materials because the cover of the simultaneous core is very small. And the thermal conductivity can be modulated between 1 to 1000 by just changing the sheath materials. And the copper silver composite tape have large thermal conductivity, which can be applied in high-field magnets. And we also found the element diffusion between different sheath materials, and this phenomenon must be avoided by adding barrier layers. Another important property of Jc is anisotropy. So there are 2 groups that measure the anisotropy parameters. They both found a very small anisotropy parameter, smaller than 2. And at low temperatures, they found the Jc with field parallel to the tape is smaller than the Jc with field perpendicular to the tape. Just opposite to the mass anisotropy. And Professor Avadi also found a reversible anisotropy at a characteristic field B star, which may be due to the field and temperature dependence of flux peeling properties. But this is still an open question of the origin of this special peeling mechanism. Okay. In my third part, I will talk about the fabrications of long-length wire and their applications. Actually, our group are continuous fabricating 100-meter long 7-core tapes by the flat rolling process, and the Jc is continuous improved. From 2016, about 10,000 ampere per square, to recently Jc is enhanced about 60,000 ampere per square at 4.2 Kelvin 10 Tesla, just by optimizing the fabrication process. And this progress is supported by the Strategic Priority Research Program of Chinese Dongliang Science. Based on the 100-meter long tapes, we fabricated the simultaneous joints by cold pressing. At last, we obtained a very high critical current ratio, about 95%. And we fabricate closed loop coils, and we use a field decay method to study the resistance. Found that there is a very low resistance, about 10-13 ohm, and it meets the application requirements in persistent model of the MI magnets. And Professor Country from the University of Cambridge, they suggest this work is undoubtedly an important step forward in the use of iron-based conductors in persistent model applications. And recent advances in the pancake coils is using the high-performance 100-meter long tapes, and at 30 Tesla, the IC is as large as 62 ampere. Is very promising for high field magnets. And we continue to cooperate with the Institute of High Energy Physics to use 100-meter long tapes to fabricate the world's first racetrack coils for the next generation accelerators. And we use metal as insulation technique, the wide and react method. And at 10 Tesla, the IC remains 87% of the shoot sample. So this is also very promising for next generation accelerators. The solenoid coils are also fabricated by the 1-2 round wire by the heat process. Professor Dongliang's group, they have fabricated nearly 20-meter long mono and 7-pole superconducting round wires, and the wires are covered by glass sleeves, and finally sintered by the hot isostatic pressing method. And here is the performance of the coil, and you can see here the field at 0 Tesla is about 3,000 ohms, and they measured many segments of the coils, and they found a very high Jc, about 71 kiloampere per second square, at 4.2 Kelvin and 10 Tesla, which is close to the Jc of the table. But the homogeneity is not very good, so there is still a large room for the enhancement of the magnetic field. Here, the Wang coating conductors are also fabricated for the long tape and coils. They use the reel-to-reel method to fabricate 1 meter long tape, and they fabricate the single pancake coils. For the short samples, the IC is about 400 ampere at 0 Tesla, and it remains, but it quickly decreased to 17 ampere at 10 Tesla, which may be caused by the weakling effect. But for the coils, the cell field, the Jc is decreased to 100 ampere, but after that, there is consistent with short samples. However, this fabrication process is very promising to fabricate high-performance coating conductors in the future. And we also cooperate with Professor Qin Xu in the Institute of High Energy Physics to fabricate the iron-based mounting cables. They have already fabricated the transport cables using the replica coating conductors, and the table reached 2,000 ampere. And for the iron-based transport cables, for now it reached 1,300 kiloampere, and they continue to increase performance of the cable. And at last, I will present that our group will fabricate a kilometer long iron-based mounting wire in Jinan, Shandong province. And there is a 3,000 square meters factory, and we have the wire drawing machine and tape loading machine, and then we have very large hot isostatic pressing furnace for the 100-meter long tapes. Okay, here's my conclusions. Currently, iron-based mounting wires and tapes are in rapid development stage of research and development. And for the short samples, there is a maximum Jc about 220,000 ampere square. And for the 1 parameter long tapes, the Jc is improved to above the 60,000 ampere square at 10 Tesla and 4.2 Kelvin. So we believe that iron-based mounting wires are very promising for applications in high-field magnetic fields. For example, at 4.2 Kelvin above 20 Tesla, or at between 20 to 30 Kelvin and above 10 Tesla. Okay, and thank you for our contributors and collaborators as well as projects and their financial support. Thank you for your attention.
Thank you, Chair. Thank you. Very nice review of the application of the iron-based superconductor. Now, session is open for the questions.
Hi, yeah, so I'm glad to see that you double Jc. How did you know that you removed the iron arsenic phase at your boundary?
You mean the high frequency one? You mean the high Jc tape?
Yeah.
Yeah, we use TM to study the grid boundaries, and they are very clean.
Okay. Yeah, because typically, I don't know what TM did you use. Is that 100% or regular TM almost?
Oh yeah, this how to say the very good TM.
Okay. Well, anyway, yeah.
Yes, can see the atoms.
Okay.
Alright, next question, please.
Very nice talk. What would you use silver? Is there any advantage? Because or doesn't it increase the cost of this? And the cost is an important factor when you make wires and long lengths of tape or conductors.
You mean why we use
Why
silver?
would you use a silver sheath and not some other element? Lower cost.
The most important thing is that the silver didn't react with iron-based conductors, but copper, iron, or even the stainless steel will react with iron-based conductors, such as element diffusion, element doping, to decrease the performance of the conductors or even induce a reaction later. But our next step is to use other sheath materials, but only for the outer sheath. The inner sheath must be silver. There is no other choice.
Okay, any other question? Okay, Jan, I just want to ask, according to your presentation, it seems like 122 is the most promising material, right?
Yeah.
Any other family of the iron-based superconductor that seems like that could be next?
So 122 is the best choice because 122 they can very easy to fabricate high purity precursor powders. And we also try the 1-1 system, the iron selenide, but the iron selenide they nearly react with every kind of sheath materials. So I also tried the 1-1 system, but the 1-1 system they cannot fabricate high purity precursors. And for the 1-144 system, they are not stable at a high temperature. So low temperature sintering, the connectivity between the grains will not very good. Okay.
Any other question? Okay, if not, then let's thank Jan for the nice